Hi everyone, and welcome back to another material science video by the Gapplebys. I'm Grace, and today I'll be joined by James and Karloot to talk about defects and diffusions.
What's going on, everyone? This is James, and I'm going to be running through some example problems where we attempt to find the amount of vacancy defects in each of our metals, aluminum and titanium. So to find the total number of sites on the right there, that is the volume of aluminum, which is 1 meter cubed, times the density of our metal, that being 2,700 kilograms per meter cubed. That's over another fraction, being the mass of aluminum, 0.02698 kilogram per mole, over Avogadro's number. To find the amount of sites with defects, we multiply that by e to the negative activation energy of 0.75 electron volts over Boltzmann constant times our temperature. Plugging these numbers into the equation, we get 6.02446 times 10 to the 28 multiplied by e to the negative 29.695-ish. That being negative puts our e into the denominator, and we get our answer of 7.65 times 10 to the 15 vacancy defects in 1 cubic meter of aluminum. Alright, flying through this one, we use the same exact formula as the previous slide. However, our mass changes to 0.04787 kilograms per mole, the amount of energy needed to form a vacancy to 1.6 eV, and our density grows to 4,506 kilograms per meter cubed. Plugging in and simplifying eventually gets us to just over 17 vacancy defects in our single cubic meter of titanium.
To find the number of Frenkel and Schottky defects in gallium, we will first need to find the number of atoms in gallium. We will calculate this by using Avogadro's number 6.022 times 10 to the 23 atoms per mole and the density of gallium, which is 5.9 grams per centimeter cubed, dividing by the atomic weight of gallium, which is 69.723 grams per mole. Calculating, we get 5.09 times 10 to the 28 atoms per meter cubed. We would then use this number of atoms to insert into our equation for activation energy. We find the activation energy by rearranging the number of vacancy formulas, giving us negative kT times natural log of number of vacancy by number of atoms. Using Boltzmann's constant, 8.62 times 10 to the negative 5 electron volts per atom times K, and the absolute temperature of 773 Kelvin gives us around 0.74 electrovolts per atom. We can then find the number of Frenkel defects by using the equation in the center. Plugging in our variables, we find that the number of Frenkel defects is around 1.97 times 10 to the 26 per meter cubed. To find the number of Schottky defects, we will use the same formulas. However, we will need to find the number of atoms plus the atomic weight of our second semiconductor, phosphorus, that is 30.973 grams per mole. When we calculate this, we get around 3.53 times 10 to the 28 atoms per meter cubed. Plugging it into our activation energy, replacing 5.09 times 10 to the 28 gives us roughly about 0.72 electron volts per atom. We can then use this amount and the number of atoms to find the number of Schottky defects, giving us around 1.59 times 10 to the 26 Schottky defects per meter cubed. To find the number of Frenkel and Schottky defects in phosphorus, we will need to find the number of atoms in phosphorus. We will do this by calculating Avogadro's number and multiplying phosphorus density, which is 2.16 grams per centimeter cubed. Dividing by this, the atomic weight of phosphorus is around 30.973 grams per mole, giving us 4.20 times 10 to the 28 atoms per meter cubed. We will then use this number of atoms to insert into our equation for Frenkel activation energy. The activation energy of phosphorus is 2 electron volts. Plugging into our equation, we find that there is 4.0 times 10 to the 28 Frenkel defects per meter cubed. Now, using what we have learned in the previous slide, we can find the number of Schottky defects by calculating the activation energy. To do this, we will plug in our new variables such as temperature, number of vacancy, and the number of atoms into our activation energy, which gives us around 1.23 electron volts per atom. Plugging into our Schottky defects equation shows that there is roughly 3.35 times 10 to the 28 Schottky defects per meter cubed.
Next, we're going to talk about diffusion length. Diffusion length refers to the distance a particle travels while diffusing. We're going to do two examples, one for our metal aluminum and the same example but with our semiconductor gallium. In each example, we're going to observe how temperature affects the diffusion length of a particle. First, we're going to look at the diffusion length of a carbon atom in aluminum after 1 minute at 300 degrees Kelvin. The formula for this is given as diffusion length equals the square root of the diffusion constant multiplied by time. Except we don't know the diffusion constant, so we can start by solving for that, which is given by the pre-exponential factor d0 multiplied the exponential of negative activation energy divided by the ideal gas constant multiplied by temperature. Next, in order to use this formula, we need a couple of constants for this situation that we found after doing some research. After we plug these constants in where they belong in our equation, we find the diffusion constant in this case is approximately equal to 5.309 times 10 to the negative 41 meters per second squared. Now, if we take this along with t equals 60 seconds and plug it back into our formula for diffusion length, we find that the diffusion length of a carbon atom in aluminum after 1 minute at 300 degrees Kelvin is about 5.644 times 10 to the negative 20 meters. Now we can repeat this process, but instead of plugging in 300 degrees Kelvin to our equation for the diffusion constant, we use 600 degrees, and we get the diffusion constant to be about 2.304 times 10 to the negative 23 meters per second squared. We can plug this into our equation for diffusion length, and we get that at 600 degrees Kelvin, the carbon atom in aluminum diffuses about 3.718 times 10 to the negative 11 meters. As we can see, at a higher temperature, the carbon atom travels a greater distance, which is consistent with the fact that particles have more energy at higher temperatures. Okay, now that we're familiar with the process of how to find the diffusion length of a particle, let's look at another example. This time we'll be looking at the diffusion length of silicon in our semiconductor gallium after 1 minute at both 300 and 600 degrees Kelvin. This is the same process that we followed in the last slide, so I won't go into too much detail. The main differences here are the equation constants. We are dealing with a different material here, so the constants for the material are also different. When we use these constants for silicon diffusing into gallium, we find that the diffusion length of silicon after 1 minute at 300 degrees is approximately 1.29 times 10 to the negative 7 meters, and for the same duration of time at 600 degrees is about 9.99 times 10 to the negative 6 meters. Again, consistent with our conclusion on the last slide, that particles move further at higher temperatures. Thank you for watching.